So let's talk about AI. Is that new tool you're using actually a genius, or is it just a really, really good memorizer? That's the big question we're going to dig into.
Right, so how do we actually build an AI that can think? One that can tackle brand new problems, not just spit back answers it's already seen. It's almost like a detective story, and we're about to go looking for the clues.
All right, first up, let's think of AI as just a pattern-finding machine. And we're going to start with a super simple, relatable problem. Can we predict a student's exam grade just by knowing how many hours they studied? Seems plausible, right?
Okay, here's our evidence, our first set of clues. It's just a simple table. On one side, you've got hours studied, and on the other, the exam grade. And you can probably already spot the pattern, right? The more you study, the higher the grade, generally speaking. And really, that's all machine learning is at its heart. Finding a way to describe that pattern with math.
But how do we make that pattern, official? How do we turn it into something a computer can use? Well, our first tool is something called linear regression. And I want you to just picture it like a mathematical ruler. Its job is to find the one single straight line that best cuts through all those data points.
And boom, once the math is done, this is what our model spits out. It comes up with a neat little formula. Basically, it predicts a student's grade will be around 55 points to start, plus an extra 4.76 points for every single hour they hit the books. We call this an interpretable model because we can look right inside and see exactly how it's thinking.
Okay, so we've got ourselves a model, but is it any good? I mean, how do we even know? That brings us to the next big question. How do we actually score its success? We need some kind of report card for our AI. So the main tool for this is something called R-squared. Yeah, it has a fancy name, coefficient of determination, but don't let that fool you. All it really tells us is how much of the difference in grades can be explained by the hours a student puts in. Just think of it like a grade for our model, a score from 0 to 100%. Simple as.
And our score is 85%. Not bad, huh? That's pretty high. It means our model, just by looking at study hours, can explain 85% of why grades go up or down. So it really feels like we've built a genius model here, right? Well, hold on a second, not so fast. And this is where we hit the big twist in our detective story. We're about to walk right into the memorization trap. This is where we find out why a great score can actually be a terrible sign.
See, here's the fundamental problem. R-squared has this really bad habit. It always goes up anytime you add more information to your model. It doesn't matter if that information is totally useless. It just rewards complexity for complexity's sake, not for being smarter.
Let me put it this way. Think about two students getting ready for a big test. You've got the genius who actually gets the material. They understand the concept so they can answer new questions they've never seen before. Then you've got the memorizer. This student just crams the answers from the practice exam. They look amazing on the practice test, right? But then they get to the real exam and they completely bomb it. This is exactly what can happen to our AI. One of our sources put it perfectly, if a little colorfully. They said, this kind of model is just mugging up by harding the answers. It's not really learning anything. It's just mimicking. A parrot, not a professor.
And there's a formal name for this problem in the world of AI. It's called overfitting. It's what happens when a model learns the practice material, the training data, so perfectly, including all its weird little quirks and noise, that it just can't handle anything new. It's our star student from the practice round who just can't pass the final exam.
So how do we catch this little memorizer in the act? Well, we use a really clever trick called the train test split. It's actually super simple. We take all our data and we split it into two piles. We let the model study from, say, 75% of it. That's its training set. But, and this is the key, we hide the last 25%. That becomes the surprise final exam. We use it to see how the model really performs on questions it's never ever seen before.
This whole idea leads us to one of the most important concepts in all of machine learning. It's called the bias-variance trade-off. You can think of this as the ultimate detective's guide for diagnosing what's going on with our model. So, as detectives, we're looking for two main clues. The first clue is called bias. That's just a fancy word for the errors it makes on the data it's already seen, the practice test. The second clue is variance, and that's the error it makes on the new, unseen data, the final exam. These two numbers, bias and variance, they tell us the entire story.
Okay, check out this detective's corkboard. It lays it all out. If your model is way too simple, it's going to do badly on the practice test and the final exam. That's called underfitting. Now, if it's too complex, that's our memorizer, it's going to ace the practice test, so it has low bias, but totally bomb the final exam, meaning high variance. That's the overfitting we've been talking about. The sweet spot, the one we're always aiming for, is right there in the middle. Low error on both. That's a good fit.
All right, so we know the problem, we know how to spot it, so what do we do about it? How do we actually fix it? Well, that's where building a truly robust model comes in. It's all about using the right tools for the job.
First off, we need a smarter way to measure success. So let me introduce you to adjusted R-squared. This is the hero of our story. Unlike its cousin, the original R-squared, this version actually penalizes the model for adding useless junk. It's like a tough but fair judge that can't be fooled just by adding more complexity.
And this is where you really see its power in action. Watch what happens when we start adding totally useless information to our model. See? The regular R-squared just keeps creeping up, trying to trick us into thinking the model's getting better. But look over at adjusted R-squared. After a point, it starts to drop. That's the alarm bell right there. It's screaming at us that these new additions are actually making our model dumber, not smarter. And finally, before we ever let our model out into the real world, we have to run a few last quality control checks. These are the core assumptions. We have to ask, is the relationship we're modeling really a straight line? Are our different inputs actually independent of each other, or are they messing with one another? And maybe most importantly, are the model's mistakes totally random, or is there some kind of hidden pattern in its errors? Answering these questions, that's the final crucial step to building a model you can actually trust.
So I'll leave you with this one thought. The next time you hear someone bragging about a powerful new AI, don't just ask them how well it learned. Ask them how well it was tested. Because at the end of the day, the difference between a genius and a good memorizer, well, that's everything.